It's my pleasure to announce Lorenz Richter. He did his PhD at Technical University of Cottbus, is now at Zuse Institute Berlin, and also has a successful startup called DIDA. And today he will talk about an optimal control perspective on diffusion-based generative modeling leading to robust numerical methods. The stage is yours.
Yeah, thanks very much, Julius. Thanks so much for having me. Thanks for inviting me. I'm super happy to be here for the first time actually at Caltech. And I'm happy that some people showed up. And please feel free to interrupt and ask questions at any time during the talk. I'm quite a bit flexible with speed and everything. And since I don't know all your backgrounds, just don't hesitate. So as Julius said, I will try to give you an optimal control perspective on diffusion-based generative modeling. And in general, in this talk, I will try to connect different branches of mathematics, namely sampling, optimal control, PDEs, and path space measures. And I guess some of these connections are kind of obvious, but others are maybe not so standard. So on the one hand, there's something maybe theoretically new, but eventually we really hope that these different perspectives on the same problem will lead to new numerical algorithms. So this is really something that we are after in the end. Yeah, before going into detail, I should mention that this work is heavily jointly done with Julius and also with Nick Niskin from King's College. So the task in generative modeling, let's say, is to sample from a high-dimensional, potentially multimodal distribution D, and I would say one can, in principle, distinguish two different kinds. Namely, either the distribution D could be given could be defined by a bunch of samples. So I really have, I hope you can see this a bit. So I have a bunch of data samples available, like these images here, and the task would then be that I want to sample from this distribution some new artificial samples. But then there's a different setting, which is basically that I have no data samples available, but I have some unnormalized density given. Right? So I don't have data samples, but I have this density given, and I would say this setting is more prominent in, say, Bayesian statistics, computational physics, chemistry, so generally speaking in the sciences. And I guess you all know that the first kind of regime has already experienced multiple very impressive results in the last years with different attempts at generative modeling. However, we want to focus more on the second case. So we really are interested in the setting where we don't have any data samples available, but only this unnormalized density, and we want to generate samples from the distribution. Right? So this is kind of the general setting, and now I want to make this a little bit more formal and try to explain you what our setup is. So we aim for sampling via diffusions, and I tried to draw a little picture here. So we want to sample from some distribution which is given or specified by this P target here, which consists of an unnormalized density rho and a normalization constant Z. And I just draw some distribution here, so this is just one-dimensional. In principle, of course, we're interested in multi-dimensional settings, but this could be a density that I'm interested in, and I want to sample from this density via a diffusion process, which could look a little bit like this. So it goes from some initial time to some capital time. And I want the diffusion process in such a way that at the terminal time, the process is distributed exactly as my target density that I'm interested in. So this is really the goal, right? So the key question will be, how do I find such a diffusion process that fulfills this task? Of course, if I sample the diffusion process, I have to start somewhere. So basically, I start at some initial density. And so you can understand this problem as somehow transporting this initial density to the terminal density via a diffusion process. To make this a bit more formal, so we are interested in diffusion processes defined by stochastic differential equations, which I define as follows here. So this is a controlled SDE, if you want, which has a fixed drift f, and it has a control function u, and then there's a sigma, which is basically the diffusion coefficient, and the sigma in front of the u is just for cosmetic reasons, so it's not so important, but it basically specifies my noise. And I let this process start at the prior density. And now the big question is, how do I find this control function u, such that when I start in the initial density, the process ends up in the final density. And as probably many of you already know, the key idea in diffusion-based generative modeling is based on the concept of time reversal. Right? So this is really important now for the remainder of the talk, so you should really pay attention to this slide. So what I do now is I introduce another process, which I call y. And this y process has a different control called v. And as kind of indicated by this arrow here, it goes from right to left. So it should really be understood as a process that starts at my target density and shall end up at the initial density. So as also written down here, so it starts at the target, and it shall basically flow inverse in time to the initial density. It looks a bit similar in the form. I mean, it will become more clear why it looks like this, but for now, just note that there's a control v here that shall fulfill this task. Okay, so now I have these two processes, and now the key idea of this kind of general setup is that we want to learn the controls u and v such that these two processes, xu and yv, are exactly the time reversals with respect to each other. Right? So I want xu to be the time reversal of yv and vice versa then, of course. Why do I want this? Because if I have this, then this immediately applies by definition basically that my x capital Tu, so at the terminal time, is distributed according to the p target. Also, I would have that yt is distributed according to the prior, but I'm not very much interested in this. So you can think of this y process as some kind of helper process, which I don't really need in the end. But what I really want is this here. And so if I can somehow find controls u and v, such that the time reversal property is fulfilled, then I'm done. Then I can sample from my target density. Okay, this is kind of the general setup. So this would be a good time to ask general questions. Otherwise, I would go a little bit more into detail. So I just continue. So now the whole talk will be about how can we actually find algorithms and how can we solve this problem and how can we better understand it. And before going into the general case, I want to consider a special case, which I guess many of you know, namely score-based generative modeling. So I just fix the v control of the y process to be 0, right? And basically I just copied the two SDEs from the previous slide, and now they give me these two equations where the second one doesn't have the control v anymore. Okay, and so now here the trick is that I can choose my fixed drift function f in a clever way, such that even without applying any additional control, when starting at the target, this will approximately end up at the prior density. Right? And the generic choice that people usually do is to consider some kind of linear drift, which then corresponds to a so-called Ornstein-Uhlenbeck process, where it's known that for infinite time, this process is exactly distributed according to a Gaussian. And so then the idea is that, well, I can't run it for infinite time, but I let it run long enough such that I'm approximately Gaussian after long enough time. And of course I can do some time scaling here and there, but the general idea really is that I choose this f function such that at time capital T, this y process is approximately Gaussian. Right? And now, I can basically do time reversal again, and I just put a picture here to illustrate this a bit. I mean, this is kind of a non-fancy version of what you can really do, but I think it helps to better understand. So basically here, this could be a target density, which is only two-dimensional, but multimodal. So this would be the y0 process. And now if I look at the y process from right to left, I basically let the particles diffuse from right to left, and they end up at something that is approximately Gaussian. So here at the bottom you see the corresponding drift up to time scaling in this case actually. And the task would be to learn this U here, so the control of the forward process. And here, well, I already gave you the solution, so this is how it would look like, such that we basically can transport, kind of move this Gaussian process, this Gaussian to this target density. Okay. So now the question is, how do we solve this problem? And I mean, this is nothing new, but I try to give you a new perspective. Yeah, there's a question.
This could be a very basic question, but could you explain once more the motivation of adding another control function v instead of just taking it as zero?
That's a very good question. So there are a couple of reasons, but the main reason, one big reason is that here we only get the approximate Gaussian distribution at capital T, and the V process, kind of, at least in theory, up to discretization and so on, allows us to end up at the Gaussian exactly. So basically the V process takes care of exactly reaching the prior density. So that's one advantage. And there are some other connections we can then also do when having the V process, which I will comment on later. But yeah, from an applied perspective, maybe that's a pretty big reason.
And you can use arbitrary priors.
That's a good point, yeah. So I don't have to use a Gaussian. Right? So maybe I want to use something more educated, so I know about my problem, and I know where my modes are. Maybe it's multimodal and I know this in advance, so I can just take that as my prior. Whereas in this setting, let me go back. So here, it really needs to be approximately Gaussian. Yeah, thanks for the question. Okay, so in this setting, the task is to learn this control U, and luckily this task has already been solved actually more than 40 years ago. So basically, it is well known that the time reversal of such a process here can be achieved by this function here, which is usually called the squared function. It's the gradient of the logarithm of the density of the y process at time t. And with this arrow, I basically denote time reversal. So I just evaluate it not at small t, but capital T minus small t. Right? And so this is basically the solution, which, as I said, has been known for some time, that is known to solve this task. So to solve the time reversal task, if I have an uncontrolled y process. Right? And so basically when we saw this the first time, we immediately thought of this control setting, and we wanted to make this connection a bit more rigorous. And so we could do this by looking at this function here, log p of y, so the log density. And this gives us a nice observation. Namely, we can see that if we look at this, actually the negative log density, which we call v here for convenience, that this function here fulfills a PDE. And the PDE is written down here. You don't have to understand the exact details, but maybe note that there are some linear terms here, and then there's a nonlinear term, and it has some terminal condition. And yeah, if you are somewhat familiar with optimal control theory, I guess you would realize or kind of recognize this equation immediately, because it's a so-called Hamilton-Jacobi-Bellman PDE, which is just a typical form of PDE that directly relates to a stochastic optimal control problem. Right? So this kind of basically will, on the next slide, open the door to the exact formulation of the optimal control problem. But even not thinking about the optimal control setting, this is, I think, already nice, because we have now connected this sampling task to basically the task of solving a PDE. So now if you're a PDE guy, you could just say, I like PDEs, I like to solve this PDE, and if I can somehow do this, then I've solved the sampling task. Right? Of course, it's very hard to solve high-dimensional PDEs, so that's another story, but now I could choose any PDE method I like, I don't know, pins, tensor trains, whatever, and I could run my machinery, and then I would get my optimal control. That's my function. Right, so, okay, never mind.
But I have a question. Please. So you solve this PDE to get the log density, but if you want to sample from log density, you still have to say run MCMC or other particle system to simulate the density, right?
No. So basically, if I get the log density, that's one. So I get the log density, this one, right? If I solve PDE, and then I know that my optimal control is the gradient of this. So then I take the gradient, which I can do sometime. I mean, let's say autodiff, and then I have the optimal control. And this, go ahead.
How will you implement the constraint condition when p-target is the thing you don't have?
Okay, so you need that, basically. So, the pointer somehow vanishes sometimes, I don't know why, but, so this, you mean this determinant condition. Yeah, this you really need. So this PDE perspective only helps in the setting when you have a density. Okay. And this is the task that we want to consider. And this is, I think, a task that is the usual task in like many science problems, right? So if I'm a molecular dynamics person, I want to compute certain energies of my molecule or whatever, then I want to sample from some Gibbs distribution, say, in order to understand certain configurational details or so.
And just to point then that the fact that your density is not normalized doesn't matter because you're taking a log and then taking a gradient.
Now I get the point. So yeah, so actually we will not need the normalized version. So I wrote this down here just for convenience, but it will turn out that it's okay to take only the unnormalized version. And you can see it already a bit here. So basically you take the gradient here again, right? So the normalization constant will disappear. Okay. Further questions? Then I just continue. Yeah, this now, as I said, so we have this PDE now, and this now allows us to, basically take the next step to the exact control formulation, because we can simply read it off from the PDE. And this basically gives us a method, which we also give a name, call it DIS, for diffusion, time reverse diffusion sampling. So basically the statement looks as this. So we have our controlled process again. Don't know why this pointer sometimes works, sometimes doesn't. Okay. Do you have a pointer actually? Because I think it's kind of.
You need to use your finger.
Okay, that's fine. So basically, you have this, this controlled process again. Or maybe I can do it like this. Yeah. And so it's the same as before. And now we can basically define or read off from the PDE a loss function, which I call L here, and it looks like this. So it contains some running costs, which appear in this integral here, and it contains some terminal costs, right? And so with this cost functional, actually, we have defined the control problem, right? So we note that the terminal cost depends on at this time on rho, actually, not on the normalized, but on the unnormalized version. And the running costs depends also on some stuff. It's not so important. It has this 1.5 u squared term here, which you often have in control problems, actually. But so with this, we have defined a control objective, which we can minimize in such a way that basically the unique minimum is attained when solving this generative modeling task, right? So it's the same as before. So basically, this u squared, this u star term here, this optimal u, is again given by the gradient of the scale gradient of the log density. Okay, so this basically says that this problem, can be rewritten down as a classical control problem. And then there's another nice correspondence, which will probably become even clearer when we look at the more general case, but I still wanted to comment on this already. Namely, one can also write this loss function here as a KL divergence between so-called path space measures. So what I mean with this PXU is the path space measure of the control process XU. So it's a path on the space of continuous trajectories of my stochastic process, right? And maybe the first version here doesn't say so much. Basically, it says a little, but it says that basically I can write it as a KL divergence. But the second one is maybe more interesting. It basically says that I can write it as the KL divergence of two path space measures, where the target path space measure is the time reversed Y process, and the PXU is the process that I want to fit. Right? So basically, this says as we expect, that we want to learn the XU to be the time reversal of the Y process. There's also a second term here which basically corresponds to some kind of prior loss, as we call it. So this corresponds exactly to the approximation of your terminal terminal time of the Y process. So if it's Gaussian exactly the Y process, then this would be 0. But usually it's not exactly Gaussian, so this would be non-zero, and it would bring in some additional error. Okay, but I think maybe more important is the fact to realize that now we have basically formalized the control problem. Yeah, and before going into the more general case, I want to make a little bit of a detour by commenting on the case that I guess most people are more familiar with, namely the setting where you have data samples but no density. And I basically want to make the argument that you arrive exactly at the same loss, or the same quantity that people usually consider in practice. So let us now, just for a couple of minutes, consider the case where we don't have the density but we have data samples. And then clearly the previous loss is not feasible, as you already observed, because we have a term in there that we don't know, namely the density. So we cannot minimize this divergence directly. So now people do a trick, or you can see it like this, is doing this trick that instead of minimizing this KL divergence between PXU and PY time reversed, you basically flip the arguments of the KL divergence. Note that the KL divergence is not symmetric, right? So this is a different thing. And instead of time reversing the Y process, you reverse the controlled XU process, right? So why can we do this in this setting? Well, if we have data samples, then we can basically simulate the Y process because we have samples at time 0, and so this is something we can actually work with, which is not the case in the setting where we don't have data samples. Okay, so we can just write it like this, and still try to minimize this quantity, which then basically, if you just plug it in, yields this control objective here, if you want, or this objective. And then you see another problem, namely in this on the right hand side here, there appears a quantity pxtu, which you also don't know. So this is the density of the controlled U process at time capital T. And this is of course something we never know in closed form. So we have to do another trick. So this is not practical. To do another trick, instead of minimizing this divergence directly, we can maximize the elbow. And the elbow basically means that you put this term here to the other side, so you get this inequality here, which holds for any U. And I mean, the nice thing is that for U being U star, the inequality turns to an equality, so that it is sufficient to optimize the right-hand side here. And on the right-hand side, there only appear quantities that we know, that we can evaluate, and that we can in principle implement. So I should note maybe that this is nothing new. I mean, we didn't do it for the first time. This has been known before, but this now follows immediately from the control perspective. Right? So you just write down the control perspective, and you get this immediately, more or less. Then maybe another comment. So if you are a practitioner, then you probably know that this is also something you wouldn't implement on your computer in order to create pictures of cats and dogs. But what you do is actually you have another even more simple version of this, where you don't need to simulate trajectories, and basically don't have this divergence term and so on. And just to comment on this, I mean, it's not super essential for the remainder of the talk, but for the experts, so you can also basically write this quantity that we had before by noting that this is kind of a constant term, by noting that you can use the so-called divergence theorem, and by noting that we can basically use a Monte Carlo approximation of the time integral, that we can write this exactly as this form here. And this maybe looks a bit more familiar to you or to some of you, because this is exactly the denoising score matching objective that people more or less use in practice, where here this Py tau given y naught is the transition density of the forward process, which for the Ornstein-Uhlenbeck process is known analytically. So this is a conditional density, which is important. And so this is, I can readily implement on my computer. I just wanted to make the point that basically, in principle, one could derive really this loss that people take in practice via the control theory argument directly. So you don't need any kind of additional tricks or so. And this is kind of, this is exact. Okay, so now I would switch back again to the problem we're actually interested in, and come back to the sampling setting where we don't have data samples but a density. And now I want to consider the general case. So recall that we have a controlled X process here, which has the U control, and we have this controlled Y process. And now the question is, how do we find U and V simultaneously, basically? And now we take another perspective in order to solve this problem, namely the path space perspective. So we consider, as I commented on before already, path space measures, which I denote here by PXU and PYV time reversed. So again, these are path space measures on the space of continuous trajectories. And now remember what I said in the first 3-4 minutes, that basically the whole idea is that I want the Y process to be the time reversal of the X process, or vice versa. And so now I can just simply write this down, right? So I can say I want that the path space measures of XU agree with the path space measure agrees with the path space measure of Y V time reversed. And so what I could do is I could minimize the divergence between these two path space measures, right? And if I can do this, and if I can bring this to 0 and I have a unique minimizer, then I have solved the task, basically, right? So by divergence, I really mean a divergence in the classical sense, so something that is 0 if and only if I have solved the task, and greater or equal than 0 besides that. Okay, so this now might appear a little bit abstract, but in the next line we will see that this actually leads to a very practical thing. And I think this is kind of the cool observation that one can compute the so-called let's say likelihood ratio for these path space measures between XU and YV time reversed more or less explicitly. And so this is called Radon-Nicotin derivative. So you could think of this as a likelihood ratio of two measures. Or let's say if there are densities, it would be easy to understand. You just compute the ratio, right? But you can also write this down for path space measures. And you don't have to understand the formula, so don't bother with the details. But the important thing to note is that what's written here is something that is very explicit in U and V. Right? So this is something you can immediately implement on your computer, because you know how to discretize integrals. So this is a deterministic integral, this is a stochastic integral. You can choose approximations for your functions u, v. There's also w, on which I will comment in a minute. And you know your densities, p prior and p type. So this is really something you can implement. Note that there's this xw thing here. So this is actually the argument of this likelihood ratio, and this already hints at a kind of cool thing, namely that we can plug in arbitrary, more or less arbitrary stochastic processes there. So this W can be yet another control that doesn't have to agree with U and V. And this will turn out to be a nice property which we will appreciate hopefully on the next slides. But so from this you should take that, well, we can do this. We can write it as a divergence minimization problem, and in these problems you usually need these likelihood ratios, and these ones we can compute explicitly. Maybe before going into the more implementational aspects or numerical aspects, let me make the comment that this optimization problem of minimizing U and V simultaneously, unfortunately, or maybe fortunately, is in general not unique. this maybe becomes already intuitive. If you think of this problem, you have a target and a prior, you want to have some kind of bridge, and then there are many bridges, right? So it can go all the way up, it can go short way, so this is all fine. I just have to end up at my target again, right? And yeah, so mathematically speaking, U and V are in general not unique, but there are a couple of ways to make the problem unique. One we have already seen just 10 minutes ago by fixing the control V to be 0. This then gives us a unique problem. We can use time reversals of suitable reference processes, so I don't have time now to explain this, but this basically relates to some other methods that other people have suggested, which are called PIS or DDS, which I will also refer to in my numerics section. Or we could relate our problem to the famous so-called Schrödinger bridge problem by adding some additional control costs, or adding some kind of regularizer on the path space measure between the controlled process and the uncontrolled process, which corresponds to this term here. And one could add this to the control problem, for instance, by Lagrange multipliers, or maybe in some other ways. So in some sense, it's some kind of constrained optimization, right? So I want this general divergence to be 0. This is my constraint. And at the same time, I want this cost here as small as possible, right? And so with this, I have exactly what is called the Schrödinger problem, which has been around now, I guess, for 90 years or so. And yeah, which then would also give me a unique solution. There's a comment, but maybe from the numerical perspective, maybe it's even fine to accept non-uniqueness. Maybe it's even good because we have more possible solutions that lead to what we actually want, namely sampling from the target. So now I want to discuss how we make this more concrete. And if we now want to really implement something, we need to choose a divergence, right? And so one very popular choice is the so-called Kullback-Leibler divergence, which I wrote down here, so the KL divergence. So this is just this one, so this one I could take. However, we argue that it could be beneficial to take another divergence, which we propose, and we call this divergence the log variance divergence, and it's defined as follows. So the divergence of the log variance, the log variance divergence between two path space measures, as written down here, is the variance of the logarithm of the likelihood ratio of these two densities, right? Evaluated at some xw. And here you already see that this is actually not the divergence, but it's a family of divergences parameterized in the function w. So for each w, I have a different divergence in some sense, and I can take this w freely. I can choose this freely. Okay? So this is a divergence in the classical sense. Of course, I need some conditions to be fulfilled, but which are usually fulfilled in practice. And before going a bit into detail, you can already see or get a feeling maybe about one or two nice properties, potentially nice properties of this divergence. First of all, the chance to choose this W freely allows us, in principle at least, to balance exploration and exploitation. It's a typical problem in optimal control or reinforcement learning, if you want. So basically, I can decide where my data shall go to, right? So I can choose any W, and I don't have to do it on policy, as people call it. I can also do it off policy. And I don't need to differentiate through the SDE solver, because I don't need to differentiate with respect to W. Right? And then there's another kind of interesting observation, namely there's a pretty direct correspondence between the log variance divergence and the Kullback-Leibler divergence, which is the following. So if I take the gradient, so with this here I denote the functional derivative, so you can think of a Gateau derivative, or also just think of a gradient. You parameterize the u with some parameter and you take the gradient, so this is the derivative. So if I compute the derivative with respect to u, and after taking the derivative I set w to be u, then up to scaling this is exactly the same as taking the derivative of the KL divergence with respect to u. Right? So this is kind of a funny observation. So the gradients agree. So now you might be confused because I just said we like the log variance better, but now I say they're kind of the same. So where's the catch? The catch is that this statement here holds in expectation, if you want. So if you had infinitely many samples, then this would be exactly the same. However, in your simulation, of course, you need to approximate everything with samples and have Monte Carlo estimators. And this then kind of leads us to looking at these Monte Carlo estimators, and I denote them with a little hat here. And so with this DLV hat, I denote the Monte Carlo estimator. And one can show that this derivative of the estimated loss function or estimated divergence can be interpreted, or is actually a control variate version of the gradient of the KL version. And the control variate, for people who don't know it, is some kind of very well-known method for reducing the variance of a Monte Carlo estimator. And the key idea is that if I have a random variable x, I define the control variate version as the same x plus some other quantity which has expectation 0. So then the two things agree in expectation, they're the same, but the statistical properties might be quite different. In particular, I might have much lower variance of my control variate version. Okay? And this is really something we can see often, not always, but very often in numerical simulations, where you see that really when taking this log variance loss, we can get reduced fluctuations basically in the optimization. So here I plot the gradient step and I look at the KL metric, and one time I choose the log variance loss and one time the KL based loss. And you can see that the log variance loss on one hand fluctuates way less and also goes down more, which is probably a result of the smaller variance. The optimization is much easier. Right. So of course I chose an illustrative example here, so it's not always as drastic as this, but usually we observe that it leads to faster and better conversions of gradient-based optimization. Then there are some other nice properties which we call robustness properties. And so basically this statement says that if you take the gradient of your log variance divergence, so let's say with respect to u or with respect to v, and you are at your solution, u being u star or v being v star, and you do this of your Monte Carlo estimator, which of course usually has some variance, then in this case it doesn't have any variance, so the variance of this quantity of this gradient at the solution is exactly 0. So this is a property that in machine learning sometimes is called sticking the landing. It's a funny name. But so basically means that when you do optimization and you kind of get closer to your optimum, and if in principle you were at your optimal solution exactly, then you would really stay there. So there would be no fluctuations anymore that could kick you out of your optimum anymore. And the interesting thing is that this is not true for the KL divergence in general. I mean, one can fix this somehow, but in principle it's not true for the KL divergence, but true for the log variance divergence by design, basically. And there's another nice property which we call robustness in high dimensions. Basically this says that if you look at product measures and you look at the relative error, so the square root of the variance of the estimator divided by the expectation of this estimator, then this relative error of the log variance divergence can be bounded independent of the dimension d. And this is, I would say, this is definitely not a sufficient condition, but I would say it's a necessary condition if you want to solve very high dimensional problems. And this is actually also true for the KL divergence, but it's not true for any divergence. So maybe you know this psi squared divergence, so for this divergence this would not be true, actually. Okay, so now I'm coming to an end slowly, and at the very end I want to briefly show you some preliminary work that we are currently working on, and which is also something that particularly comes handy with the log variance loss. Namely, the log variance loss, or log variance divergence, allows us to consider what we call sub-trajectories. So instead of simulating entire trajectories, which might be kind of costly, we might want to only simulate small trajectories, not from 0 to t, but from t0 to t1, so they could be much, much smaller. And we want to basically design an algorithm that can only build on these subtrajectories, which might be might have advantages from numerical perspectives due to multiple reasons, which I will comment on later. And so now we could define a loss function. So this is not super well written down, but I hope you know what I mean. So basically, on a time interval t0 to t1, which also gets the u and the v, and now it gets a different quantity, which I call p tilde here, which has the task to kind of approximate my density of the controlled process at these times t0 and t1, because instead of having p prior and p target, I now am somewhere in the middle, so I don't have p prior and p target anymore, so I need p of t0 and p of t1, so to speak, which I don't have, but now I can just approximate this additionally with this p tilde here. So this p tilde aims to approximate eventually actually the density of the optimally controlled forward process at a time t. And now we can, maybe I should comment, so the nice thing about the log variance loss is now that we can actually do this because we can take our reference, the process that we evaluate the divergence along, we can take this arbitrarily, right? So this xw, we can choose it freely. If we had the KL divergence here, this would not work, because then we would need to be able to start the process at xu at time t0, and this of course we can't do because we don't know much about this density, neither can we sample from these. So this doesn't work with the KL divergence, at least not that I know. Then one can massage things a little bit and make this objective a little bit nicer by, this is now getting very detailed, but I just want to give you a glimpse of it, by using the so-called Nelson's relation, which basically says that the sum of the optimal u and v is given by this score here. And so we can exploit this quantity and say, well, now instead of learning this p tilde, we try to learn the log of this, basically, which we call phi. And then we can also learn v, and then u follows from this relation automatically. Right? So we just rearrange terms and would get the corresponding u. And so this would result in a loss that only depends on two quantities again. This phi here and the v. You don't have to understand the exact formula here. I didn't even write down the exact definitions, but the key point here is that even with subtrajectories, we can get a loss that depends only on these two quantities here. And then in simulations, we could choose these subtrajectories actually randomly. So the t0 and the t1, we could just vary this either randomly or by some more clever choice. Okay, so now at the end, I would briefly show you some numerical examples. And I should maybe note that we're still more in a say proof of concept phase, maybe a bit more than proof of concept, but we are currently working on scaling this to more high-dimensional problems even. But yeah, I think there's still some nice observations. So just to show you some pictures, and as you might have guessed, so in practice we usually parameterize u and v by neural networks and do gradient descent. And in the numerics, I want to basically compare now different loss functions or different divergences, namely the KL divergence and the log variance divergence, and I want to compare different methods, which I didn't explain in detail, but they basically relate to what I said, namely the PIS method, which is a method that was around before, and the DIS method, which is one of our methods, and this SB method for Schrödinger bridge, which is our kind of general method. And so here, I look at a Gaussian mixture, which is kind of admittedly not the most challenging problem in 2 dimensions, but it's already not so difficult because it contains 9 modes, and I think if you would run certain other sampling tasks like MC, it might get stuck in modes and so on. And so here we can already see some nice observations. So this is the ground truth here. Maybe look at the pictures first. This is the ground truth. And here we display the results of our sampling algorithm when either using the KL divergence in PIS, or the log variance on PIS, or the KL divergence on DIS and the log variance on DIS. And you can see that in this example, the log variance loss performed much better, particularly with respect to detecting the different modes of the sampling problem. So I'm not saying that it's not possible to do it better with the other methods. Of course, you always kind of tune your methods maybe so differently, but no, I mean, we try to be quite fair. So this worked out of the box more or less for the log variance loss and not for the KL. And then there are some metrics here. So we look at the difference of the log normalizing constant, because in this toy example we can compute a reference value explicitly, so we can just compare. We look at some Wasserstein true metric, we look at the essential sample size, and we look at some difference in the standard deviation of the marginals, which basically quantifies mode collapse a little bit. And you can see that, I mean, not in all values, but in most values, the log variance loss is quite a bit better than the KL-based loss. Just for fun, I mean, we looked at this two-dimensional density, which has actually a lot of modes, and so really, I mean, think of this as a two-dimensional density. This is the ground truth, and we can see again that the log variance loss yields to quite significantly better performance compared to the KL-based loss. And then we also looked at, say, a double well or actually multi-well problem, which is kind of popular in molecular dynamics applications, where also we can see that log variance loss is slightly better, and maybe it's even more illustrative to look at the pictures here, where we can see again that when using the log variance loss here and here, either for the DIS or PIS method, we can recover the modes quite a bit better, and in this case the loss doesn't suffer from mode collapse. Here's the promised example of this preliminary work with the subtrajectories. Basically, we see a nice advantage of this attempt. To be honest, I mean, of course, we designed this setting a little bit in such a way that subtrajectories might be helpful, but I think it's still kind of a realistic setting, namely where the prior density, which is displayed here with these dots here, doesn't share a lot of support with the target density, which is the surrounding density here, which in this case is a two-dimensional Gaussian mixture with 40 modes. So the dimensionality is kind of small, but the different modes might actually make the sampling problem pretty difficult. And I guess MC-MC methods could get stuck in modes very easily. And here, basically, when looking at the KL or log variance loss metric, then we are not able to discover all the modes readily. I mean, the log variance loss is a little bit better in mode exploration, but still also not perfect. And when doing this subtrajectory attempt, where we can now basically freely sample the space better, where we basically make use of this exploration idea, then we can really identify basically all the modes of this problem. So in particular, when the prior and target don't overlap well, this might be a promising direction to follow. Yeah, looking at the time, I hope we are good, and I think I would like to conclude now. So what we have done, or what I tried to tell you about, is a connection between optimal control, PDEs, path-based measures, and the now very famous diffusion-based generative modeling, which is kind of nice from a theoretical point of view, but also from a practical point of view, because this now immediately allows to carry over respective methods from one to the other perspective. We have introduced implementable algorithms, which allow us to sample from unnormalized densities, which are, I should have mentioned this more, are already competitive to alternative, more standard methods like MC-MC and sequential Monte Carlo. We have seen that this log variance divergence very often outperforms the KL divergence. that's basically the key observations. And then there are many interesting further research directions. For instance, the Schrödinger bridge problem, which I mentioned. So we haven't implemented this yet. This might be quite interesting. One should probably study exploration versus exploitation behaviors even more and think about how to come up with more clever ideas to explore the space a bit less naively, I would say. Then one can exploit this PDE perspective a bit more, for instance, by solving PDEs with different methods like pins or tensor trains. One could, of course, consider different divergences. So basically, this framework now works with any divergence. So you give me a divergence, and I can implement this with your favorite divergence, and we can see if it works better. As seen just on the last slides, we don't need to simulate entire trajectories anymore, but we can consider sub-trajectories. And of course, the long-term goal is to scale this to more challenging, more high-dimensional problems, but it's not so easy, and there are still some also engineering aspects, I guess, to tackle. So with this, I thank you a lot for your attention. Here are the references, and now feel free to ask any questions if you have them. Yeah.
I have a couple of questions. First, does this log variance method only work in the unnormalized distribution case, or does it also can you also adapt it to give better results in the sampling, in the samples case?
That's a very good question, and I should have made this clear. So it only works, at least to best of my understanding, in the setting where you have the unnormalized density, unfortunately. So in this generative modeling attempt that people usually study, where you have data samples, I guess this is what you meant, we cannot use the log variance divergence. In fact, I think we cannot use any divergence because the divergence needs the target density. You can use the elbow, so you can use some kind of related objectives, but you can't use the divergence.
And, my other question is something that has been of fairly recent interest in the, again, in the data samples case, is solving inverse problems, so sampling from conditional distributions. Does that also carry over in this context, where can you use this method now in the scientific cases that you're interested in for maybe solving scientific inverse problems by sampling?
I think this could be a really nice field to explore. I mean, to be honest, myself, I'm not so familiar with the setting there, so I cannot give you a precise answer. But I think, there might be very direct connections, and I think it would be a nice follow-up to see how we could apply this there. So I cannot give you a better, I don't know if maybe Julius knows better, but I'm not super familiar with the setting. But I mean, if you have something in mind, we could certainly discuss this. You have a complete idea. Yeah. Other questions?
So in the end, when you said if you go back a slide, on explore, exploit, how are you, I guess the question is always the reward function, right? For the right explore, exploit trade-offs. So how are you thinking of that?
Yeah, that's a good question. So, I guess one thing is the sub-trajectory thing, where you can basically, there can be a combination of random exploration and then, like, maybe gradually you switch to more exploitation, but then it's getting a bit more, it's not super systematic anymore, right? So you need to just, do a little bit.
And also in high dimensions, that random exploration will take forever, right?
That's true. So, I think, there's no free lunch, right? So you cannot expect that you discover immediately every mode of a very high-dimensional problem. But the hope is a bit that with this we get at least a bit better in terms of exploration, better than, for instance, KL-based methods, which are known to suffer from this mode collapse. But we thought a little bit about naive exploration strategies, and the sub-trajectory idea that's already worked quite well. But to be honest, other ideas also didn't work out of the box. So by just taking this W which I mentioned before, kind of in a more random way, we also found that sometimes it didn't work well. So it's not so easy, I think. So if anyone has if you have a good idea, let us know. But I think maybe one comment, so with this connection to optimal control now, we can talk to the reinforcement learning people. I mean, this is basically the same setup, right? I mean, I think really more or less exactly the same. It's a bit more specific, so reinforcement learning is even more general, right? But we can talk to these guys, and maybe they give us some advice, and we can now combine these methods and use them for sampling.
Yeah. Again, if it's something like LQ or LQG, you can come up with strategies, and there's even optimal regret bounds, and one of my former students worked on that. But I guess in this case, it's all non-linear, right?
Yeah.
And we don't know the optimal answers.
Yeah,
I mean, it's hard.
It's pretty hard. Yeah, but I think there are many ways to just try out things also a bit. I mean, to explore the exploration strategies. And I'm serious. I mean, I think it would be a next a good idea to talk to reinforcement learning people more and to try out their methods and see if there's some improvement.
I mean, there are intuitions, for instance, like, in the beginning you should explore more. So there, we were worried a lot about stabilization, right? So you want to first make sure you can control it that is stabilizing, and so you'd rather explore. So I don't know how you would translate those kind of notes.
That's a good comment, and I think also that one nice thing is that with this W, which we can choose freely, we can always choose a combination of some random thing and the on-policy U, right? So we can say, well, we take a bunch of particles with a policy and a bunch of particles randomly. So this is out of the box possible, right? It would be nice. Thanks. Further questions?
No further questions. We thank our speaker again. And thank you everyone for coming.
Thank you. And don't hesitate to send me an email if you have further questions. Right on time.